Hello everyone and welcome back to my channel. In this video I'm going to talk about the transitive closure of a graph. Here is an example. We have this graph G, which is a directed one, although the algorithm that we have here will work both for undirected and directed graph. However, the example I provided here is a directed one. So at the middle of the screen you see the adjacency matrix of this graph G, which says that if there is an edge that goes from a node or the vertex I to the vertex J or not. For example, as you see here, there is an edge from the node C or the vertex C to D and K. So the entries here for the like the C to the D and K is equal to 1. So we're assuming that 0 means there is no direct edge or there is no edge, and 1 means there is an edge from the source index vertex to the destination vertex. So what is the transitive closure and what is the Floyd-Warshall algorithm that we're going to discuss today? So the transitive closure of a graph is about finding out if there is a path from one node to another node, or from one vertex to another vertex in the graph. So for sure, if there is a direct edge, there is a path. However, we're going to find out if there is not a direct edge from one node or one vertex to another one. Can we find if there is a path or not? So a very simple algorithm that we're going to discuss today is the Floyd-Warshall, which is very simple. It contains 3 for loops, and it uses the adjacency matrix as the basis to create another matrix called the transitive closure, which we're gonna, in this example, we're gonna call it the matrix T. So the matrix T will be initialized with the adjacency matrix data. So because we need to know that which are the current the connections between the vertices. So the Floyd-Warshall algorithm, as I said, contains 3 loop structures. So it is like the nested loops, and I and J are I is the source vertex and J is the destination vertex, and K is any intermediate vertex that will connect I and J together. Another word, K is the vertex that is in the path of going from the vertex I to the vertex J. So it is very simple. As you see here, for the first for loop has the K, and we have the I and J in the internal loop structures. So here, the reason that we have the K, or this intermediate node is written at the first loop, is because for every I and J, we're going to repeat the process of finding out if there is if there is a path from I to J for every possible intermediate vertex. Here, as you see, I and J, for example, if I is equal to 2 and J equals to 3, and these are just the keys or numbers that we're associating with each node or each vertex. For example, here what I can do, I can just put 1 associate 1 here to be 2, 3, 4, and 5. So when I say I is equal to 2, I mean the node B, and when I say J equal to 3, I mean the node D. So I want to see that if there is a path from B to D or not. And by K equal to 1 up to N, it means that I'm going to try every other node, for example the node A, K, and C, and to find out if there is a path using any of these nodes as the intermediate nodes. So that's why the K, or this for loop, is written like above, because I'm going to repeat this question here, or this process of finding out if there is a path from I to J. Otherwise, if I had the K, the for loop for the K after the I and J loop structure, this will not just give me the accurate answer. So it's really straightforward what we're doing here. This is a statement that you see here. I'm going to just to talk about it, explain it. Here it says the T of I and J, which we're going to store if there is a path from I, the node I to node J or not. So it's going to store either the value 1 or 0. And here it says this is equal to T of I and J, which means that if there is already a path, I'm going to store that one, or we're going to see if we can go from the node I to K, or there is a path from node I to K, and if there is a path from the node K to J. So again, just using an intermediate like the node, just to see that if I can connect the node I to J or not. So I'm going to talk about the time complexity of this algorithm, this Floyd-Warshall. As you see, there are 3 for loops, 3 nested for loops. The first one will go from k equal to 1 to n. Same thing for the I equal to 1 to n and j equal to 1 to n. And n is the number of vertices that I have in the tree, in the graph. So in other words, the size of the vertices is equal to n. So and because again, that's going to just find about the connections between the vertices, so that's why it goes up to n. And I'm going to try to find the relationship or this transitive closure for every node of the graph. So it's very clear to see that because we have a nested for loops that all of them go from 1 to n, and each one of them, each of them we're gonna repeat n times. So the time complexity will be from the big O of n cube, again because of the nested loop structures that I see here. So which is a polynomial time, still not bad, but the degree of the polynomial function is 3, so it's still manageable, but for larger graphs with like the more or the higher value for n, it's gonna take more time to calculate the like the transitive closure. Although maybe we can just do some adjustment to the code, or implement it more efficiently. But here is again just a very simple version of the the Floyd-Warshall. So here I'm gonna just just do part of this one here, because n in this example is equal to 5. So n is equal to 5. That means that Floyd-Warshall algorithm, we're gonna do 5 cube, which is 125. So in order to find the transitive closure of this graph, I have to check or run this statement that we see here 125 times, which will not be efficient to do it in this window. For sure, you can just implement this algorithm. Is going to be very easy. Maybe in just a few milliseconds or seconds, you're going to see the result. But I'm going to show you just part of the like the solution. So here let's say that again I is equal to 2 and j is equal to 3, and I'm going to show with different values for the k that how it works here. Or maybe I can just choose j equal to 4, because there is no direct path, so it might be a better example here. So assuming that we are I is equal to 2, which is the node B, and the j is equal to 4, which is the node C, and I'm going to see if there is a path from the node B to C or not. So one way is that, as I said, by using the k equal to 1, and k is equal to means that it is the node A. So as you will see here, that there is no path, or in other words, the T of B up to the node A here is equal to 0, because so far we found that there's no path from B to A. And then for sure, if I'm going to use the AND operator with any other one, it will not going to work. But anyway, I'm going to just write it. It's going to be T of A to the node C, which is also in this, so far we have found it is 0. So it's going to be 0, and using the node A, at least so far we found that there is no path, although we can find that later when we just run the whole algorithm that there is. The next one, this time I'm going to use the k equal to 3 actually, and not the k equal to 2, because it's the node B itself. It's going to just repeat the statement. So instead I'm going to use the k equal to 3, which is the node D. So the T of B to D and from the node D to node C. Let's see what's about this one. T of B to D is if there is a path or an edge from B to D, which is the case, so it is 1, and also from D to C, which as you see also in the transitive closure there is. So both 1 and 1, which means true and true, and means that there is a path from the node B to the node C. So that's again just a very simple example of the way that the algorithm works. So by updating the entry in the matrix for the B and the D, next time if we're gonna find for example, if there is a path from B to C, if we're gonna find that if there is a path from B to K, also we will, we can just easily see that from B we can just go to C. So there is a path from B to C. So we can use the node C as the intermediate node going from B to the node K. So maybe also I had to choose another index, so do not confuse this K here that I wrote here with this K or this K here. This is the name of the node, but here is just an index. So don't confuse that one. But again, just when you repeat these for loops, that's going to help us even for for more nodes. It's going to work properly as again. So from B to K, this time I can use the node C as the intermediate node because there is a path from B to C, from to C, and from C to K as well. So I'm going to just draw the transitive closure of this one very quickly just to see that how it works. For sure, again, we need just to for larger graphs with more nodes, it's going to be even harder to draw, but again, that's not hard, just to see that how it works. So I'm going to start with again with the graph itself. So here we have the node K, and here I have the node D, and here I have the node C, and these are the connections that I had here. There was from A to B, and then from here, and there was this connection I had here. So and I'm gonna just draw the edges that's going to be added as part of the transitive closure with the color red here. So we found that there is a path from A to B, and also there is a path from A to D using the node B. So I'm going to add this edge here. Then from A to C there is a path through A to B, and then to D, and then to C. So I'm going to add this edge here as well. Let's see about if I can go from A to K, and this is the case because from A I can go to B, then to D, and then to C, and then to K. So also I'm going to add this edge here as part of the transitive closure. Now, can I go from A to itself? That's the case because I can go from A to B, and then from B to D, and from D to C, and from C to K, and from K to A. So there's going to be a reflexive edge here from A to itself. What about B? From B, can I go to A? And the answer is true because from B I can go to D, and then from D to C, and C to K, and K to A. So there is one here. So can I go from B to A itself? From to B itself? That's true because I can go from B to A and from A to B. So also there's gonna be the reflexive edge here. Now, can I go from B to C? The answer is again yes, because I can take the node D, so there is an edge here. Can I go from B to D? The answer is correct again, because I can go to C and then K. And so I have almost everything that I need. So what about the node like the D? Can I go from D to the node A? The answer is correct, because from D I can go to C, C to K, and C to A. So I can add another edge here. Can I go from the node D to itself? The answer is correct, because I can go to C and go back. So there's a reflexive edge here. Can I go to the node B? The answer is correct, because I can take the node A to go to the B. So there is an edge here. I know that is going to be maybe not very good looking, but that's how the transitive closure going to work. We're just going to see that if there is a path from one node to another one. So and then we're going to see if there is a path from D to K. The answer is yes, because we can go from D to C and C to K. So here's also that one. So I think I just wrote everything for the D. And for the node C, we know that we can go to the node like the D, and from D we're able to go to any other node. So that means that from C we can go to itself, we can go to the K, we can go to the node A, and also we can go to the node B. So that's the same thing from the node K. We can go to any other node. So here also I'm going to add this one here, also I'm going to add this one here, and also the vice versa. And also from the node K we can go to itself as well. So in this example it was possible to actually or we can see that all the entries in the transitive closure matrix is R1, because there is a path from any node to any other node of the graph, including self, so all of them is work. But that's not the case all the time. For sure you can just write examples that not all trees are one. For example, if we have this graph, let's call it G1, and here we have the node C, and if you look at this one, this graph that we have here, graph G1, the transitive closure says there is a path from C to B and C to A, but for sure from A we cannot go to itself or going to C or going to B. So again, just to make sure it works properly, we need to run or use this algorithm such as the Floyd-Warshall algorithm, which is going to again work in the big graph n cube to find out the transitive closure of a graph. Please watch my other videos about the graphs, about the trees and other data structures that might be useful for you.